So I'm going to talk today about a method that uses something called quasi-velocities, and a popular and efficient way to get equations of motion that skips the step of having Lagrange multipliers. As much as I want you to know Lagrange multipliers, they can be a pain and they're confusing and, right? So if possible, we want to avoid them. But anytime you have a system with constraints, so this is let me give, the usual way. I don't know what happened there. The usual way, so using Lagrange multipliers. And why do we use Lagrange multipliers? Anytime we have constraints. And whether they be holonomic or non-holonomic, they can always be written in the non-holonomic form. So we can always write them, any constraints present. And let's say that we have S of them, following the terminology of the Kasman Paley book. We could always write them in this form where it's a sum over our n, little n generalized coordinates, ALI QI dot plus ALT equals 0, where L, this index L, goes from 1 to S. Okay, and these, ALI might be a function of Q, and ALT might be a function of the Q's as well. So we've got these constraints. So we've got S constraint equations. In the usual way of doing it. And then Lagrange's equations, you write the Lagrangian function, so kinetic minus potential, and any non-conservative forces you would include in a generalized non-conservative force. And so you've got these Lagrange's equations. And then the forces of constraint are handled via these Lagrange multipliers. So we sum over the constraints, and there's these lambda L's, and then ALI. And this, there are n of these. So we have n Lagrange equations. And the way that I've told you to think about this is, so we've got n plus s equations, and the n plus s unknowns are our q's, the double dots. So q1 double dot to qn double dot, and then these s Lagrange multipliers. Okay, n plus S equations and n plus s unknowns. And that's a lot of equations. That's a lot of unknowns. And wouldn't it be great if we could somehow get some minimal set? So just skip the whole step of getting Lagrange multipliers, even for the case of non-holonomic constraints, so stuff with the rolling and things like that. Well, there is a method. It involves something called quasi-velocities. So that's what we're going to talk about. So you should know this stuff about the Lagrange multipliers. I'm not saying, skip that. It's good to know. And one reason is because if you ever need to find out what the constraint forces are, right? This is we call this like CI, the generalized force of constraint. So if you do need to find out the generalized force of constraint, you got to go through this Lagrange multiplier step. But if you don't care, and you just want to get the dynamical equation, you just want to know what the motion looks like, a more and more popular method is this thing called quasi-velocities, and the dynamical equations associated with it are sometimes called Kane's method, developed by, I think, a Stanford professor named Kane, not too long ago in the history of mechanics, like 1960s. So there's still innovations happening, even in classical mechanics. So let's talk about quasi-velocities. And the good reference for this Greenwood discusses this very well in his section 4.1. So Kazan and Paley mention it, but they do not go into the depth of Greenwood. So I'd say if you want to read up on it, it's Greenwood. So a quasi-velocity, we just sort of introduce quantities. These are variables called quasi-velocities. And they are, we will have n of them, just like there are n generalized coordinates. And the terminology is to use little u. So little u sub j is going to be a sum over 1, I goes from 1 to n, so of some function. This is a capital psi, ji, which is a function possibly of the q's and time times the qi dots, and then possibly some other thing over here that's not linear in the qi's. And there are, so this index j goes from 1 to n. So we've got quasi-velocities. They are functions of the real velocities. I guess we could say that they're functions of the generalized, these things, the qi dots, the generalized velocities. But sometimes they're more useful than the generalized velocities. Why are they called quasi-velocities? They're called quasi-velocities because they aren't the time rate of change of any quantity. They are just a linear sum of time rates of change of actual coordinates, but they are not themselves the time derivative. So it's not like, so uj is not the time derivative of something. It's just not. If it was, then it would be a genuine velocity, but it's not. So it's a quasi-velocity, okay? I'll show you an example soon. You've seen these. They get used. Another important thing is that they are invertible. So these n equations are invertible to give the QIs the QI dots as a function of the U's. So QI dot equals, I'll use the same notation as Greenwood. So it's the sum over, and now this is capital phi ij, which will also be a function of q's and t's, uj plus phi I t q, function of q and t, and I goes from 1 to n. You could cast everything that I've written here in terms of the matrices. So if we think of this capital phi, I'll put 2 underscores to emphasize it's an n by n matrix. It's a square matrix. And phi as a matrix is just I call it psi inverse and phi it is this thing. You can get it from psi jt. Okay. So you have seen quasi-velocities. We've used them before without calling them that. When we did rigid body dynamics. When we looked at Euler angles and their rates of change, right? We use Euler angles. If you're to describe the rotational degrees of freedom for a rigid body, you would use Euler angles. And right, I'm just putting these generic theta 1, theta 2, and theta 3 because there's 12 different types of Euler angles. But they have their rates of change. These would be the generalized. So if these thetas are the generalized coordinates, their rates are generalized velocities. Oops. But to write the dynamics, it was always easier to write things in terms of body axis components of the angular velocity. So the equations of motion looked nicer. In fact, they were just more compact. There were fewer of them with the body fixed, or let's just say body axis components of the angular velocity vector. Right, omega 1, omega 2, omega 3. And then Euler's rotational equations of motion were related to omega 1 dot equals something, omega 2 dot equals something, omega 3 dot equals something. And the relationship between these looked exactly like these two formulas up here. So if you remember, so for example, for the 3, 2, 3 Euler angles, we could write what? Oops, I'm trying to insert something. Yeah. Right, we would write these are the body fixed components of the angular velocity vector written in terms of the Euler angles and their time rates of change. So this is exactly looking like this equation up here, where the QI dots are these Euler angle rates. And you can see that the components of this actually do depend on the generalized coordinates Q. And then of course we could write its inverse, which was something else. You can invert the matrix, and then you would get something like this, right? So we've seen this before. We just didn't call it quasi-velocities at the time, but this just means that this sort of procedure generalizes. So you can, and if we wrote the Lagrange's equations for the Euler angles, so we get a Lagrangian that's a function of what do we have here for the 3, 2, 3 Euler angles? Psi theta phi and psi dot theta dot phi dot. This gives us what? 3 second order ordinary differential equations. And each second order ODE can be turned into 2 first order ODEs. So we got from this 6 first order ordinary differential equations. But everything was a lot easier if we just did the Euler's rotational equations in terms of these omegas, the body fixed, or the body axis components of the angular velocity. In which case, right, we had omega 1 dot equals something, omega 2 dot equals something, omega 3 dot equals something. And this something over here, these are all, you know, functions of the omegas, not the thetas. And there were only 3 of them. So we only had 3 first order ordinary differential equations to get at the dynamics. So there's this savings in terms of the number of equations of motion you need if you pick these quasi-velocities correctly. And here, like we call this, these are quasi-velocities because omega 1 dot is not the time rate of change of any coordinate. So it's not a velocity, but it is linear in velocities. It's a function of velocities. Okay. So the big deal and the big savings happens. I guess this is kind of one example. I could give another. If you know anything about aircraft dynamics, and I don't, but maybe you do. But I am told that when you do aircraft dynamics, you typically will write the velocity of your aircraft, right? This inertial velocity of the aircraft, let's say the center of mass with respect to some, you know, origin on the ground. That gets written in terms of body axes components of this velocity. And I think it's, you know, right, u b1 plus v b2 plus w b3. And so these u, v, and w are quasi-velocities. They're not the time rate of change of like if this was x, y, and z. They're not x dot, y dot, z dot, but it is more convenient for doing aircraft dynamics. And I'm guessing in like a junior level aircraft dynamics class, they don't say, oh, these are quasi-velocities. It's part of a more general theory, but it is. Okay. The method really shines when you have constraints, so that you get to avoid the whole Lagrange multiplier situation, which is really nice. And so how is that done? Let me just sneak up here. And if you look at this equation, let me erase this thing. Look at this equation. And it has a very similar form. We've got something that's, you know, linear in the qi dots plus maybe some other term. That looks a lot like these constraint equations, at least the left-hand side of them. So you could actually pick quasi-velocities. You pick some quasi-velocities so that they are exactly in the direction of these constraints, so that they're always equal to 0. And then the remaining quasi-velocities are free to vary. So that's sort of the trick. So we, when constraints are present, you can skip Lagrange multipliers. Which is a wonderful thing. It's a wonderful thing. So we will choose, here's what you do. You choose the last S quasi-velocities, right? And because out of n, right, we have as many quasi-velocities as generalized coordinates. So we'll pick the last S of them to be the left-hand side of the constrained equations. And that means, so the first n minus S are unconstrained. Means they're independent and will give us the dynamics. Okay, so let me just summarize this. Uj equals sum 1 through n, capital psi ji, function of q and t, qi dot plus psi jt qt. Here j goes from 1 to n minus s. So these are the unconstrained ones. Unconstrained. And then the kind of constraint based will be the last grouping. I'll still write it as uj. Sum I goes from 1 to n, capital psi ji qt qi dot plus psi jt qt. Here j goes from n minus s plus 1 all the way up to n. And we pick these very specially where, this thing, psi j I equals a. Remember the a's come from the constraints. So we'll write this as a, subscript is j minus n plus s, right? A had, I think, 2 subscripts. So this is the first one, and then this is the second one. And psi jt equals a, j minus n plus s t. Okay, so we've picked for the last s quasi-velocities, we're just picking these coefficients so that they exactly match the constraints, in which case these all equal 0. So if you wanted to get the qi dots, qi dot equals, now this is a sum from j goes from 1 to n minus s. All you have to do is consider the ones that aren't equal to 0. This will be phi I j qt uj. But remember, the last grouping of them equals 0, so we just don't even include them in the sum. Plus phi I t qt. And here the index I goes from 1 to n. So we will get dynamical equations for the n minus s unconstrained U's. So what's the savings? Before, with the Lagrange multiplier, we had n plus s equations that we had to solve for. Now we've actually improved things. We've subtracted negative 2s from that. So now it's only n minus s. So that's a big savings in terms of computing this. We still haven't written what the dynamical equations are, but let's do that. So this is now, and Kane's name gets associated with this. So I'll just write it as Kane's equations of motion. You might also, if you've seen anything about this, there's the name Jourdain, who did something in the early 1900s. I think he wrote a principle, but Kane's name seems to be more associated with it now. But it's basically just using D'Alembert's principle, but with using quasi-velocities to write everything. So we're basically just going back to Newton's laws. But here's what we do. So we write the, let me write it out. We write the translational velocity of, and we're thinking of a set of multiple rigid bodies in general. So we'll write the translational velocity of body I center of mass. So I'll write it this way, velocity. And now I'm following the notation of Greenwood. So he writes VCI, and this is a sum. J goes from 1 to n minus s, because we're going to be doing a sum over quasi-velocities. It's a vector, gamma I j u j plus gamma I t. I guess I should emphasize what these q's could possibly be functions. I mean, these gammas could be functions of q's and t's. And this will be a gamma vector that does not pre-multiply a quasi-velocity. So here the index I goes from 1 to the number of rigid bodies. So we're talking about n rigid bodies or particles. So if it's just particles, then you'll skip the part that's related to angular velocity. And you'll notice this gamma ij, is this the same as the projection vectors from before? Well, kind of. But we're writing it as it's the partial of the velocity partial the quasi-velocity now. So it is a quasi-velocity coefficient. And we'll do an example so you can see this. This is equation, if you're following in Greenwood, it's equation 4.125. Okay, that's the translational velocity of body I. The angular velocity or rotational velocity for rigid bodies, we write it as omega sub I. It's the angular velocity of body I is the sum over all of the non-zero or unconstrained quasi-velocities, and this using the same notation as before, I'll write beta here. Beta ij could be a function of the q's in time. Uj plus beta I t qt. Again, the index I is over the body, so 1 through capital N. This is equation 4.136 in Greenwood. Beta ij is partial omega I partial uj. So we call this the angular velocity coefficient. And then the heart of the matter, where the dynamics comes from, the dynamics equation comes from D'Alembert's principle. So you literally use D'Alembert's principle to get the equations of motion. So this, if you remember from D'Alembert's principle, we did a sum over the bodies of basically taking the projection of, this is massive particle I, this is the inertial velocity of the center of mass. The inertial derivative of the inertial velocity of particle I minus the applied forces on particle or body I dotted with gamma ij, then plus, we do the inertial derivative of the angular velocity, particle or body I minus the moment about the center of mass, the applied moment, dotted with beta ij. And that equals 0. How many of these are there? So here we're going from j was from 1 to n minus s. So this D'Alembert's principle this will give, it'll end up getting first order ODEs for the U's. Which is pretty cool. And the resulting equations will have a certain form. So the resulting equations will have the form, there'll be a mass matrix times the U's made into a column vector. That's U dot there, plus F, another column vector, Q, U, T. So this is a matrix equation. There it is. U is just a column vector, U1 all the way down to U. Remember, this only goes to n minus s. Those are the only ones that matter. F is n minus s column vector. And m is n minus s times n minus s. And I think it's positive definite. I don't know. I can't recall right now. But this is a way of summing up these n minus s first order first order dynamical ODEs. Totally get to skip Lagrange multipliers. So this is now, there's software that automates this, which is nice if you've got some kind of complicated system, especially if you've got constraints. What did it require? Well, you've got to know the applied force, you got to know the applied moment, and you have to pick some quasi-velocities. So let's try this on an example. All right. I think that would be good. Are there questions up to this point? It could be the example will help clarify, but questions yet? No. All right. Well, I'm glad you're hanging in there. I don't know if you had a double shot of espresso, but this kind of stuff needs it. Although, I mean, this is pretty exciting, this reduction of the equations of motion, only n minus s. Your advisor will be impressed. Maybe not. I don't know. Yeah, let's look at an example and something we've seen before. I like to use the batons, not the baton falling off the wall, although, you know, maybe. Now we'll look at the our old friend, the baton with a wheel under it thing. Like, what is going on here? Dr. Ross and his weird toy models. Yeah, so this is the baton with a wheel under it. One mass. So this is just a two particle system, which means in the equation of motion, we'll only be looking at this part because we'll just have two particles. But we first have to set it up right. So this is what we've usually been given. We need to, I mean, if you remember, what was the constraint? The constraint was that there's, if, you know, velocity, the velocity of particle one couldn't be in, oh, it's pretty big. It couldn't be in the n hat direction. So if you do n hat dotted with v1 equals 0 was the constraint. And it gave us something of the form x dot minus sine theta plus y dot cosine theta equals 0. I guess we should remind ourselves what the Q's are here. So we've got three Q's. The set of Q's are x, y, and theta. So n equals 3. We've got one constraint, so s equals 1. So the way that we did it before, we had n plus s equations with n plus s unknowns, and it was the second order derivatives of each of these, and then the one Lagrange multiplier. But now we get to skip all that if we pick things right. So we'll pick, remember what the procedure is. We're going to have n quasi-velocities. We pick the last quasi-velocity to equal this. So u3 equals that. And then there's a u1 and a u2. What are we going to pick for those? So for u1, we could pick the velocity that's along here. So we'll just call that maybe v. I'll call it v. And it equals, I'll write it this way, so that's kind of nice and clear. Cosine theta times x dot plus sine theta y dot. That's what that direction is. So this is, kind of the procedure here is that we're looking for things that are, I don't know why this does that. I don't like that. I'll use this blue. Here's the E1 along the body, and here's E2 perpendicular to it. So this is essentially the the E1 component of the velocity for V1. It's really the only velocity that's allowed, right? Because the projection over here has to be 0, so we only get that direction. Okay, what about U2? U2 is a very good band from Ireland. But we can pick, let's pick theta dot. So this fits the form of a set of quasi-velocities. It fits the form up above, and we've picked U3 to exactly be the direction in which there's no motion, equal to 0. So if we go with this, we need to be able to write the velocities of each of the particles. Remember, from up here, let me sneak up here for a little bit. So looking at this, we need to be able to write the velocity for our 2 particles as some linear sum of the UJs that we've chosen. So what are the velocities? Velocity particle 1. And now, so this is where it's different from the Lagrange multiplier approach, because now you're writing the velocity given the constraints. This isn't the unconstrained velocity. This is just the actual velocity of that thing. So the velocity is, it's V in the E1 direction. In other words, U1 in the E1 direction. And then notice if I took partial V1, partial U1, this equals E1. So that's exactly gamma 1, 1. So we could also write V1 equals gamma 1, 1, U1. And notice gamma, is this 1, 2, partial V1, partial U2. Well, it doesn't depend on the second quasi-velocity, so that's 0. Okay, what about velocity of particle 2? We use the fact that this is they are rigidly attached. So what is if we were to put in a inertial frame, what is the angular velocity of the E frame that's attached to the rod with respect to the inertial frame? And it is theta dot E3. So E3 is just coming out of the screen at you. So that's equal to U2 E3. So using the fact that particle 2 is rigidly attached to particle 1, there's this truth about rigid bodies. The velocity of some part of the body plus this angular velocity cross the location. Let me write it up here. This vector is the location of particle 2 with respect to particle 1. And that's how you get the velocity too. But what is, we know everything here. This is U2 E3. And what is R21? That is L E1. So we've got, what was U1? U1 is, V1 is U1, the E1 direction. And then this other thing is U2, L U2 E3 cross E1. Let's use the right-hand rule. E3 cross E1. My thumb is pointing in the E2 direction. So we've got U1, E1 plus L U2 E2. And from up above, this has to be able to be written gamma. This is 2, 1, U1 plus gamma 2, 2, U2. I'm putting a vector on U2. I shouldn't be. Okay. Gamma 2, 1 equals E1. Gamma 2, 2 equals L E2. Okay. Now let's take inertial derivatives. We've taken inertial derivatives enough that hopefully you can do this. Inertial derivative of V1 is, remember what was V1 up here? It's that. I don't even know why I introduced this V. You don't need that V. We'll write this as U1 dot E1 plus U1 inertial derivative of E1. Remember, E1 is a body fixed direction, so we have to use the transport equation. Says this is omega, the E frame with respect to the I frame cross E1. And what you'll end up with, this is U1 dot E1 plus U1 U2 E2. And just similarly, let me give you the punchline for it's the inertial velocity V2. This is U1 dot E1 plus U1 U2 E2 plus L U2 dot, and then there's a minus L U2 squared. These need directions. That is E2 minus L U2 squared E1. I'm skipping the step of you take the inertial derivative of E2 and whatnot. All right, so now we plug this into D'Alembert's principle. We have no applied forces, so that's nice, right? Looking up here, applied force on particle 1 and the applied force on particle 2. We're just assuming right now it's 0. If we wanted to, we could add something in. I don't know, some kind of driving force, but right now it's 0. So now plug into this yellow highlighted part up here, right? Mass. Let's assume equal masses for the two. And then we've already taken this inertial derivative, and then this is 0. We just have to take the dot product with these velocity coefficients. So using D'Alembert's principle, start with J equals 1. We've got the mass times the inertial derivative of V1 dotted with gamma 1, 1 plus m inertial derivative of particle 2, the inertial velocity particle 2 dotted with gamma 2, 1. This gamma 2, 1 was equal to 0. So that goes away, and this is all equal to 0. So we're just taking, whoops, this dot product. Remember what gamma 1, 1 was? Gamma 1, 1 was just equal to E1. So we're taking, let's look up here, the dot product of that thing with E1, I think. If I did this right. Oh, wait, no, hold on. Did I do it right? No, I didn't do this right. Gamma 2, 1 is not 0. Yeah, it's the same as gamma 1, 1. It's gamma 2, 1. So each of these is just E1. We're just taking the dot product of both of these with E1. So what we'll get, right, let's be U1 dot E1 plus U1, U2, E2 dotted with E1 plus U1 dot, it's E1, U1, U2, E2 plus L, U2 dot E2 minus L, U2 squared E1 dotted with E1 equals 0. All right. What do we get from here? U1 dot. What do we get from here? U1 dot minus L U2 squared equals 0. So this equation just gives us 2 U1 dot minus L U2 squared equals 0. What happened to the masses? Yeah, I guess I divide by M because M multiplies both. So this is our dynamical equation, at least one of them. If we do the second one, J equals 2, inertial derivative V1 dotted with gamma 1, 2. This is the one that's equal to 0. Plus M inertial derivative of the inertial velocity of particle 2 dotted with gamma 2, 2. And this was equal to LE2. Okay. What do we get? We end up with LU2 L squared U2 dot plus L U1 U2 equals 0. If we collect these two and put it in the matrix form, this is what we get. Yeah, L U1 U2 equals 0, 0. So it looks like what we expected. We've got a mass matrix. We've got the U dot matrix, and we've got this F matrix that we expected to be. It looks like it's not a function of the Q's. It's only a function of the U's. It's not a function of time either. There we go. And you could simulate this. So, and yeah, you could simulate this. We're skipping the whole approach of Lagrange multipliers, right? There's n minus s equals just 2 first order ODEs for the U's. Yay. If you simulate it, where do we go here? Yeah, I'm just showing here. You could code this up in Matlab. So I'm showing, notice the F and the M, and I'll provide this. But if you simulate it, you get, I use the same initial condition as I showed before for when I used Lagrange multipliers, and I get the same type of motion. So I'm able to solve for the motion, but more directly. You're like, well, hold on, you just solved for the u's. How do you get the x's? Well, from up here, you're able to invert these to get what is x and y and theta as a function of the u1 and u2. It just adds some additional first order ODEs. So we solve these dynamical equations at the same time that we solve for, I guess you can call them the kinematic equations for x dot, y dot, and theta dot. And then that, you don't need these actually to do the dynamics, but you need them if you want to know, kinematically, how did the baton progress, okay? I'll give you another example. This is a vehicle. This is related to vehicle stability in a skid. And this is a big deal when it gets icy around here. If you're on icy or snowy roads. So here is this is a sketch of a vehicle where there are wheels that are rolling without slipping. And then it's as if you have a ski up here. So this would be like the wheels that are skidding. And so a question you might ask yourself is, if I'm driving, what would I prefer? Would I prefer the front wheels to be skidding, or would I prefer the rear wheels to be skidding, as if you have a choice? But to kind of motivate this, you can look online for like cars skidding. So here's like a highlight of cars skidding in snow. So that doesn't look good. Doesn't look good. Yeah, please drive slowly. This has happened to me in Blacksburg. It's not pleasant. You don't want people to hit. Oh, look at that. Ooh, not good. And then this person, like fishtails, totally reverse. Notice that's totally reversing. Where do we see that before? Shopping cart instability. And then people have to go around. It's like, come on, man. Causing trouble here. So this is also because I think it was a Russian mechanist studied this, whose name is Chaplygin. You might say Chaplygin, but let's just say Chaplygin. So it's also called the Chaplygin sleigh. So you've got these rolling wheels. So those have there's a knife edge constraint. Meaning, write the normal vector, and there's no motion of that rear side of the car, whatever side of the car that is, in that end direction. And then this thing is able to move freely. So these are the skidding wheels. If we do a sort of above view of the situation, like here's the schematic, and we're showing body fixed directions, E1 and E2, as opposed to these sort of world fixed directions. Right, this would be like the N1 direction, and this is the N2 direction. N1, N2. It's actually more convenient to consider the velocity of the center of mass. So here's the center of mass. Here's the center of the velocity of the center of mass. This is a rigid body, so there's going to be omega, which is theta dot E3. So there's some vector coming out of the screen. The constraint back here at B, even though you've got two wheels, just consider that the point B, there's a velocity. The unconstrained velocity of the point B would look something like that. But of course, there's no velocity allowed along the axis. So the constraint, and there's just one, so S equals 1. So VB dotted with N equals 0. But N is the same as E2. So we could say because E2 is a body fixed direction. So the velocity of particle 1 dotted with E2 equals 0. What coordinates will we have? Well, if we wanted to track like the center of mass here, our set of generalized coordinates Q would be X, Y, and theta. So N equals 3, S equals 1. Before we would use Lagrange multipliers, but now we know that we could pick N minus S equals 2, pick two unconstrained quasi-velocities. And sort of taking a hint from aircraft dynamics, we'll actually just write the inertial velocity of the center of mass, but in terms of its components in the E1 and E2 directions. So this would be V1, and I'll write this as V2. And it's the same as U1 and U2. So we'll use the inertial velocity of the center of mass written in body axis components. They're quasi-velocities because they don't correspond to the time derivative of anything, but you can work it out. So what is X dot? If we were to write, this is X, this is Y. X dot is V1 cosine theta minus V2 sine theta. Y dot is V1 sine theta plus V2 cosine theta. So it exactly has the form. It's looking like V1 and V2 will work as quasi-velocities. And what's the velocity of point C? This is the center of mass here. We could either write it as X dot N1 plus Y dot N2, but equivalently, this is V1 in the E1 direction plus V2 in the E2 body fixed direction. This constraint up here involving VB, we need to use the fact this is a rigid body. So velocity particle B is the velocity of particle C plus the angular velocity cross, we have to write the location of, let's write this as RB with respect to C. For a rigid body, this is what's true for any point on it, or how the velocities are related. So if you work out this constraint up here, the start equation becomes, it says that theta dot equals V2 for B. So what do you know? We're able to write all of our generalized velocities in terms of these two quasi-velocities. So we're all set up. Then you use D'Alembert's principle to get the ODEs. And if you had some other force on here, like if there was a friction pad up here and you had to figure out what the friction was or the effect of that, that would become important. but we now use D'Alembert's principle to get the dynamical equations for V1 and V2, right? And you'll have to use the fact that this is it's a rigid body, so it's got a mass. You have to take the inertial derivative of the center of mass and then dot it with gamma. You just have one body, so 1I. I guess I'm skipping that there could be an applied force. 1I plus, you would need to write the inertial velocity of the inertial derivative of the angular momentum about the center of mass minus any applied force about the center of mass dotted with beta. The first index just means we have one body, and then the second index is the quasi-velocity. So I here is 1, 2. I think maybe before I wrote this as J, so just for don't confuse people. There we go, J. So you get your two equations of motion. Here's what they turn out to be. You get V1 dot equals V2 squared over B, and V2 dot equals negative V1 V2 over B. 1 plus IC. IC is just the moment of inertia about the E3 direction, right? Because we are taking into account this rigid body rotates over MB squared. So they look kind of strange. You could actually make a phase portrait in these V variables, and it'll give you something like this. So here's the V1 direction and the V2 direction. If you start out, with going in the V1 direction. What's the positive V1 direction? That means I'm kind of doing a sketch of a car. Right, here's E1, here's E2. It means you're going this way. V1 is positive. That's actually stable. How do I know it's stable? If I pick some other initial condition, like up here, well, I kind of go in this arc until I hit the positive V1 axis. And that is true wherever I start, I'll hit the positive V1 axis. In fact, all trajectory, if I start on this other side, I'll make some ellipse and I'll end up on the positive V1 axis. So all of these, everything on the negative V1 axis is are unstable points, and everything on the positive V1 axis are stable points. So these are, I don't know if I said that, these are unstable, a line of unstable points. And then this is a line of stable points. And so no matter where you start up here, it's going to do some elliptical arc, and it wants to end up going in the positive V1 direction. It wants to align it so the skidding wheels are in front. So this is stable. And then this other situation where The rolling without slipping wheels, if we're going that way, this is V1 less than 0, and that is totally unstable. Any slight deviation, and it's going to want to turn and go with the skidding wheels in front. I think this, you can kind of match this up with, would I prefer rear wheel drive or front wheel drive? I think the wheels that are driving tend to be the ones that skid, whereas the kind of passive ones are rolling without slipping. So you can think about that. So I think this is the front wheel drive case. I think most cars are front wheel drive. So if you got front wheel drive, good. Right? Yeah, because what's going on here? Let me just, if I were to sketch, where's E1 and E2? Kind of flipped. Just to tell you some other things, if we had, and this will be quick, like if I had this situation, I think I called this the Chaplygin racer. Because it's kind of like a roller racer, but weird. We would have, for the Q's, we have what? We're tracking the center of mass here. So X, Y, and then the orientation of that mass, and then this angle too. So we have N equals 4, but then we have S equals 2 constraints. And the 2 constraints are back here, there's no velocity allowed in this direction. And over here, there's no velocity allowed in that direction. You can work out what those are. So you get 2 constraints, which means you can end up with N minus S equals 2 unconstrained quasi-velocities, which is a big savings. So that means you just have 2 first order ODEs, which if you analyze those, you'll see something. There's actually 4 equilibria. Only one of them is stable. And it's if the wheels, the front wheels kind of tuck under the back, this thing right here is that's what I'm talking about. This one is the only stable configuration. The others are unstable. If you think of a truck hauling goods across the United States or anywhere, it's this situation, which is unstable. It's not the most unstable, but it's unstable. And this leads to jackknifing. I don't know if you've heard of jackknifing, but that's when a truck goes like this. Bad situation. You don't want that. Big accidents, jackknifing, tractor trailers. Yeah, I guess I'll end there.